Hello class, in this video I'll be going through combustion reactions and showing you how to calculate the energy output from burning fuel. A combustion reaction involves burning fuel in oxygen. Because the enthalpy of the fuel is greater than the enthalpy of the products, the combustion of fuel is an exothermic process because it releases the excess energy as heat, which is characterized by a negative delta H value. For a combustion reaction to occur, three things must be present: fuel such as a hydrocarbon, oxygen supply, and heat to initiate the combustion process. Because oxygen is a reactant in combustion, combustion reactions is an example of an oxidative process. There are many ways for us to tell whether an oxidation reaction has occurred. For instance, oxidation generally involves the loss of electrons, but we can also recognize if oxidation has taken place if oxygen was gained, which means that oxygen had to be a reactant in the chemical reaction. Combustion reactions can also be described as complete or incomplete, depending on the availability and the amount of oxygen present when it's reacting with the fuel. Complete combustion occurs when there is a plentiful supply or excess amount of oxygen reacting with fuel, and the products formed are carbon dioxide and water. In contrast, incomplete combustion occurs when there are low quantities of oxygen, which produces carbon monoxide and water. As you can see in both of the chemical equations, the fuel used in either forms of combustion is carbon-based, which can either be a hydrocarbon such as octane, or it could be an alcohol which contains oxygen atoms such as ethanol. The objective in this video is for us to learn how to calculate how much energy is released from combustion of a given amount of fuel. To do this, I'm going to need to introduce you to the concept of heat of combustion. The heat of combustion, often referred as the molar heat of combustion, is defined as the amount of heat released by 1 mole of fuel when completely burnt in oxygen, with the products being carbon dioxide gas and liquid water. The table on the right hand side shows the heat of combustion of common hydrocarbons, which can be found in the VCAR data booklet. Although we know that enthalpy change for a combustion reaction takes on a negative value, the heat of combustion values are listed as a positive value in the data booklet. This is somewhat misleading, but these values take on a positive value because the name already suggests that energy is released, hence by convention we can state the heat released by combustion as a positive value. If we are looking at a fuel that uses pure substances such as hydrogen gas, methane, or ethane, we often write the heat of combustion expressed in kilojoules per mole, but it could also be expressed in kilojoules per gram as well. Let's unpack and interpret the information presented in the table. For the complete combustion of 1 mole of hydrogen gas, this produces 282 kilojoules, whereas the combustion for 1 mole of propane gas produces 2,220 kilojoules per mole. Students often make the mistake by misinterpreting that this value is the heat released by the entire reaction or the enthalpy change. This is not the case. I would like to emphasize that the molar heat of combustion is not the same thing as the change in enthalpy. When we're dealing with mixtures or fuel blends that contains multiple components such as biodiesel or natural gas, the units for the heat of combustion is reported in kilojoules per gram instead. All of the heat of combustion values recorded on the table are measured under standard laboratory conditions. This means that the energy released was reported at room temperature of 25 degrees Celsius and 100 kilopascals. Now that we've looked at the heat of combustion, we should now be able to calculate how much energy is released when fuel is combusted. Let's use hydrogen gas as an example. According to the data booklet, we know that 1 mole of hydrogen gas releases 282 kilojoules. If I wanted to find out how much energy was released if I had 4 moles of hydrogen gas, I can simply use ratios and multiplication to find out the amounts of energy released. Thus, the energy released by 4 moles of hydrogen gas should be 4 times the amount compared to 1 mole of hydrogen gas, giving us an answer of 1,128 kilojoules. An easier way for us to do this is by using the following formula. Energy released is equal to the number of moles multiplied by the heat of combustion. Similarly, if we did 4 multiplied by 282, this will give us the same answer as 1,128 kilojoules. Let's now look at a slightly more challenging example. Most questions typically ask you to find the energy content released from a specified mass of fuel. In this example, you've got 3.6 kilograms of butane. To start off, we need to make sure that mass is in standard units, so I'll convert 3.6 kilograms into grams by multiplying it by 1000. Then I'll need to find the number of moles of butane by dividing its mass with its molar mass. This will give us an answer of 62.0689 moles. By referring to the VCAR data booklet, we know that 1 mole of butane releases 2,880 kilojoules of energy. Because we've got 62.0689 moles of butane, to find out the amount of energy released, we're going to multiply that by the molar heat of combustion, giving us an answer of 1.79 times 10 to the power of 5 kilojoules. I would now like you to have a go at answering a similar question. Pause the video now and then resume again to compare answers. To begin, we will first convert kilograms to grams by multiplying by 1000. From there, the number of moles of propane can be calculated by dividing 5400 with its molar mass, giving us an answer of 54.54 moles. According to the data booklet, 1 mole of propane releases 2220 kilojoules of energy. Hence, if we multiply the number of moles of propane reacting this question by the molar heat of combustion, this will give us an answer of 121,090.9 kilojoules. However, we need to correct 3 significant figures, hence our answer is going to be 1.21 times 10 to the power of 5 kilojoules. The next thing that I'm going to discuss is that we can actually find out what is the value of the heat of combustion when we're given its thermochemical equation. The first example shows the thermochemical equation for the combustion of methane. Because 1 mole of methane produces 890 kilojoules of energy, the heat of combustion will also take on the same value, and this is also supported by the values shown in the data booklet. In the second example, we have the thermochemical equation for the combustion of butane. According to this equation, 2 moles of butane is burned in excess air to release 5,760 kilojoules of energy. Because we are interested in the energy released by 1 mole, the heat of combustion of butane can be found by dividing the change in enthalpy by 2, giving us an answer of positive 2,880 kilojoules of energy, which is also reflected in the VCAR data booklet. I'm hoping with the second example, you can see that the heat of combustion is different from the change in enthalpy. I'll now go through a more challenging example that wants us to calculate the energy released from 45 kilograms of octane using the above thermochemical equation. This question is very similar to the other examples that we've looked at, but we need to be careful of the stoichiometric amounts. To start off, we convert kilograms into grams by multiplying by 1000. From there, we can then find the number of moles of octane by dividing by 114, giving us an answer of 3.9474 times 10 to the power of 2 moles. We know that the energy released from combustion can be found by using the following formula. In order to use this formula, we need to first find out what is the value for the heat of combustion. The heat of combustion of octane can be found by using its thermochemical equation, because in this equation, it's saying that 2 moles of octane produces 10,108. Hence, if we divide it by 2, this will give us the energy released by 1 mole of octane. Once we've found out what is the heat of combustion of octane, we can then plug in the values in this formula to therefore give us an answer of 2.0 times 10 to the 6 kilojoules, which corresponds to option C. In the last section of this video, I want to show you how to convert between the different units for the heat of combustion. As I stated earlier in the video, the heat of combustion for pure fuels can either be reported in kilojoules per mole or kilojoules per gram. If you ever encounter a question that asks you to express the heat of combustion in terms of kilojoules per gram, divide the kilojoules per mole by the molar mass of the fuel. An example is shown on the right hand side. In the table, we are given the heat of combustion for propane and octane along with the respective molar mass. Using the flowchart, we can express the heat of combustion for both of these fuels in kilojoules per gram by dividing the heat of combustion by its molar mass, giving us the following values. By now, you should be able to meet the success criteria in this video. Thank you for watching, and I'll see you guys again in the next one. Bye.